Okay, Le Chatelier's principle. Remember, the basic gist here. We're looking at a system that's at equilibrium, and we can alter things about the reaction, like the temperature, the pressure, the concentration of any of the components. And it's going to shift back to it's got to shift a direction to get back to equilibrium, and it's going to counteract the disturbance. So shifting a certain direction to reestablish equilibrium is going to be what we're looking at here. Now this first example, we're really looking at, didn't pop up. Hold on one second. Okay, practice 1. We have hydrogen iodide gas decomposing into hydrogen and iodine separate component elemental forms. The above system is at equilibrium. Identify what will happen to the partial pressures of iodine gas when the following changes occur. It's either going to increase, decrease, or remain the same. Those are your choices. And let's try to think through here. When we add stuff in, which way does it normally go? The opposite side from where you added. Good. Towards the other side, right? Yeah. When you remove stuff, what happens?
Fills the gap.
The same side.
Goes to the same side you removed it from. Good. To replace it. Very good. So let's take a look here. Now we're not just deciding which way it's going to shift. We actually need to look at the effects on the iodine gas and that partial pressure of the iodine gas here. If we add more HI in here, what's going to happen to our iodine gas? Partial pressure will increase, decrease, or remain the same. It should increase, right? Very good. Partial pressure of iodine, it should increase. Now, here's the why. Why is it going to increase?
Because it shifts towards the product side.
Adding in on the reactants is going to shift towards the product. Iodine happens to be a product, so that means the iodine amount is going to increase. Now, remember, when you add stuff in, that changes your quantities, but it's going to shift to get back to that proportion of K. So even though we're going to have different quantities, different partial pressures now, it's eventually going to get back to where it increases your products, decreases the little bit of the HI to get back to that K proportion. So think about that too. That's important. All right, we're adding more H2 to our system. What happens to our iodine in this case? It's going to decrease. I agree. Why is it going to decrease? Why is it going to decrease?
Because the reaction shifts towards the reactants.
If you add in hydrogen, which is a product, it's going to shift and go towards proceed towards the reactants. That means that it's going to consume the products to make reactants. And iodine, therefore, some of it will be consumed, and it will end up, decreasing the partial pressure. So remember, when you add in H2, that's initially going to increase. And then shifting to the left, to the reactants, will make more HI. So when the K is now calculated, you're going to have more H2 balancing out the loss of the I2, and then you'll have more of the HI, so it gets back to that K proportion. Does that make sense? Everybody kind of seeing that, kind of mentally framing that in their heads? Thinking about those values, because that would be what you would plug into the law of mass action, and it would eventually get back to that K value over time. How about if H2 is removed? Increase. Good. It will increase. Very good. If we we remove H2, that means it's going to proceed towards the products. That means we're going to make more products, so that means the partial pressure of I2 should increase. And last but not least, think about this one. We're adding more I2 to the system. Would it decrease? Would it increase? Would it remain the same? Interesting. All right. So this is the hard one to think about and really understand. We add more I2 in. Yes, it's going to shift towards the reactants, right? So it is going to go this way towards the reactants. But it has to get back to that K value. So by adding in the I2, it's going to be higher than its original equilibrium partial pressure. Shifts to the left, it is going to lose some of that, but it's still going to be higher than its original partial pressure when it establishes K. Back to that Kp. So yes, the partial pressure of the I2 is going to be increased from its original value, and that's kind of like the gauge that you need to go here. From the original I2, it's still going to be slightly more. Yes, we're going to lose some of it. It will shift and it will lose some of it, but that I2 value will still be higher than the original one that it was at beforehand. Does that make sense? So the I2 goes up, the H2 is going to definitely decrease here, and the HI is going to go up, and it's going to do that until it gets back to that Kp value. So when you multiply the products over the reactant squared, it gets back to that Kp value. Everybody go with that? All right. Now let's talk about, oh, here's the answers. The answers for you. All right. Talk about heat. Talk about changing temperature. This is the only case for any of our equilibrium constants, and there are a number of them. The only time K will change is if you change the temperature. This is because it affects the kinetics or the speed of the reaction. So it's going to change and favor one of the reactions, whether it's the forward or the reverse. So it is going to alter the ratio of the reactants to the products because the kinetics and the speed of the collisions and whatever does get altered, so you get a different proportion. The key to temperature changes. You have to be able to identify what type of reaction you have. Is it endo or exothermic? You have to be able to do that first. Now, sometimes it's as simple as this, where they just throw in heat as a reactant or heat as a product. Okay, endo as a reactant, exo if it's a product. But they don't always do that. They don't always make it that obvious. Okay? And we're going to talk about the scenarios as to when it's not that obvious. All right, so let's look here. Do you remember it follows the same kind of idea as concentration or partial pressure? If you add to a side that heat's a reactant of, or say if you add to the side where heat is, it's going to go the opposite side. If you remove from the side of the heat, you're decreasing the temperature, it's going to go towards the side that it's being removed from. So it kind of follows the same guidelines as concentration or partial pressure. Definitely that same deal. But now let's talk about how to determine what are the clues that they can give you to tell you about the reaction, whether it's exo or endo. So one of them, of course, is the delta H value, the heat of reaction. If it's endo, delta H is positive. If it's exo, delta H is negative. That's just the way it is. They could put that over to the side. It could be listed like in the top part of the FRQ. that information's given to you. It's something that you should pick up on. The next one's not so obvious, especially in a calorimetry problem. They can have a change in temperature set of data for you. And remember that the thermometer always measures from the surroundings perspective. So you change the temp, like you have an initial temperature and then the temperature decreases, so the surroundings get colder. That's going to be endothermic. Okay, so decrease in temperature, that's endothermic. Increase in temperature is going to be exothermic. And those ones show up mainly in those calorimetry problems, but that's also a way to tell you whether it's endo or exo. So don't forget that. We always like to, think we connect everything, but that's an important one to connect here. Yes and no, sort of. Just going back over stuff. Another thing here, whether or not it is in the reaction itself. They could have the word heat, but they could also use the word energy. If it's part of the products, it counts. They could also stick in a energy amount somewhere in there. It's another way to recognize whether it's endo or exo. So if energy or kilojoules is part of the products, it's exo. Energy or kilojoules is part of the reactant, it's going to be endo. But these are various ways that they can show you. The last one, probably remember from before, but it's not as obvious because we haven't really done anything with it in this unit. They could give you an energy diagram. They give you an energy diagram, you should be able to read it. Maybe this is like part A of the FRQ, and then part D or E has to do with the equilibrium now, but they expect you to remember from part A that the energy diagram's telling you, if the reactants are above the products, it's exo. If the reactants are lower than the products, it's endo. So these are various ways in the FRQs that they could tell you whether this is exo or endo. All right, so now we're going to do another practice here. This is a dissolution system here. We have magnesium sulfate solid dumped into a beaker here. Okay, it's solid. A certain amount of it's going to dissolve, but do have an idea too that there's going to be some of the magnesium sulfate solid at the bottom. And some of it dissolves into its ions, gets surrounded by the waters and all that. So, if we increase the temperature here, what is going to happen to our mass of magnesium sulfate solid there at the bottom of this beaker? What happens to the magnesium sulfate solid here? Temperature increases.
The temperature of the surroundings or the temperature of the energy?
We're increasing the temperature on it. We're heating it.
System.
We're taking this.
I get so confused with the endo and exothermic stuff.
We are taking this beaker of solution, we put it on a hot plate, and we are heating it ourselves. We're giving it heat. So, first of all, the thing you should ask yourself, is this exo or endo? Exo. So heat belongs over here, right? Heat goes on this side. That's the first thing you should ask yourself. Now, if we put this under a Bunsen burner or on the hot plate, we're adding in the heat. So this isn't where we mix it and it gives off, there's a temperature change. We're actually, this is already in a beaker. It's sitting there. Now I'm going to put it on the hot plate and heat it. So, which way is it going to proceed?
Towards the reactant.
It's going to go left, yes, this way, towards the reactants. And if it goes towards the reactants, what happens to my mass of my magnesium sulfate? The mass of the magnesium sulfate solid, okay? That mass is going to increase. Very good, because it's shifting that way towards the solid part, the not dissolved stuff. So let's look at this one. We decrease the temperature. Now we're putting it in the refrigerator. We're submerging it into like another beaker of ice, water or something. We are cooling it down ourselves. So basically, decreasing the temperature is removing heat. So what's happening?
It's going to shift towards the products.
Yes, it should shift towards the products. So what does that mean about our amount of our magnesium sulfate here? Our solid, yes, the mass of that will decrease. That decreases, that mass decreases. Now for the hardest one of the bunch. This one isn't a temperature one, but this one's kind of challenging. We're now going to take some barium nitrate and dump it into our beaker and stir it. So what's going to happen here? We dump this in there, stir it, what happens? Let's think about what we got here. We got barium nitrate, BaNO3, 2. That's barium nitrate. What do you know about nitrate compounds? They are soluble, thank you. Good. So that means this is going to dissolve, right? We're going to end up getting Ba2 plus and NO3s minuses. These are going to be floating around in there, right? What else is floating around in there right now? Already. The magnesium ion, that's floating around in there, and so is the sulfate. Yes, there's still some magnesium sulfate at the bottom together, but we do have those other two ions floating around. What's going to happen now? A reaction between which two of these ions are going to react?
BaSO4.
Yes, good. And so the suggestion here was Ba and SO4. That's going to form a bond and precipitate out. This is true, but what do we really need to know in order to determine that? What do we have to remember? In order to know what's going to cause a reaction here, we need to know our solubility rules. So sulfate's a pain because sulfate's one of the ones that has all those exceptions, right? Silver, mercury, lead are insoluble with sulfate. We also have the heavy alkaline earth metals, that's calcium, strontium, barium. They always precipitate out with sulfate too. So if the sulfate is combining with the barium and dropping to the bottom as a precipitate, what does that mean for our equilibrium system up here? What's happening here? What's being removed from the solution?
SO4.
Yes, the sulfate is being removed. This particular ion is being removed. So which way is it going to shift then?
Towards the products. So MgSO4 is going to bond.
It's going to go towards the products because the sulfate is being pulled out of solution. That means it's being removed. So if it shifts towards the products, what happens to our solid up here? it's going to
Decrease.
decrease. Good. MgSO4 solid is going to decrease in its mass. The mass decreases, okay? Remember, a dissolution system here, that if you have the powder at the bottom of the MgSO4, you take out some of the sulfate, it's going to want to replace it, so it's going to dissolve more. It's going to dissolve more of the magnesium and the sulfate. They're going to separate, and the water will absorb them, and they will become ions in solution. So that one's a particularly challenging one, but don't forget too that you can dump other things in there and alter the equilibrium system by having a reaction occur, and it might pull out one of the ions. No, the magnesium, the nitrate, those ones stay as spectators because they're not, both of them are soluble in all situations here. So the magnesium and the nitrate aren't doing anything, they're just spectating. But the barium and the sulfate do form a bond and precipitate out. So that pulls sulfate out of solution, that means more magnesium sulfate solid will dissolve. So it shifts to the right, towards the product. Definitely the most challenging one, but don't forget they could ask you stuff like this about solubility rules. And what you're going to see here in some of these problems, they're bringing in and connecting other concepts into the equilibrium problems. So kind of reviewing other stuff from other units too, like this would be unit 4 stuff. So yeah, it all comes together now. Now let's talk pressure. Let's review some pressure stuff. Obvious one, what's not going to cause a shift in equilibrium? Adding the inert gas. That one doesn't change anything, right? The inert gas isn't going to react with your reactants or your products. So the amount of partial pressure for those things are going to stay the same. The only thing an inert gas will do if you add it to the vessel is it's going to increase the overall pressure of the vessel. The pressure of the entire mixture will go up. But the individual partial pressures of those that are in the equilibrium system will remain the same. This one's not so obvious, and I don't know if I pointed it out well enough last time, but when you have equal moles of gas on both sides of the reaction, there will not be any shift in equilibrium. The idea, the way that it shifts, if you increase the pressure, it shifts to the side with fewer moles, so that can relieve some of the pressure and get back to that Kp. And then if you decrease the pressure, it shifts to the side with more moles to get back to that Kp value. But here, if it's equal moles, it's not going to do anything. Then Kp equals Kc, and you won't have any kind of shift here. So Boyles Law, don't forget this one. Oops. Remember, pressure, volume are inversely proportional. So talk about it in terms of volume. So decreasing volume increases pressure, goes to the side with fewer moles. So remember this, fewer moles. And then if you increase the volume, that means the pressure will decrease and it will go to the side with more moles. So yeah, this is where Boyles Law gets thrown in. P1, V1 equals P2, V2. Don't forget that inverse relationship there, kind of important. And of course the opposite's true. Increasing volume decreases pressure, proceeds to the side that has more moles of gas. Once again, in order to get back to that Kp value, to get to the ratio of the products over reactants, reestablishing Kp proportions. So that should seem pretty obvious. All right, that one just kind of throws it all together for you again. We just said that, so I'll move on to the practice. Here we go, practice. The above system has reached equilibrium. which way will the reaction proceed when following stresses are placed on the system? First one, the volume of our reaction vessel is increased.
Towards the reactant side.
Towards the reactant side. For increasing, that is true. It's going to proceed towards the reactants. Now, why is that?
Because there's 3 moles on the reactant side and only 2 on the product side.
Good. So the first thing you should do when you see one of these problems is count your moles. 2, 1, we have 3 moles. On the reactant side, over here, we have 2 moles. And yes, this only applies to gases, because gases are the only ones that exert the pressure. So we would go towards the reactants, towards the side with more moles to get back to that Kp ratio and the pressure. How about adding argon? 15 moles of argon. It's not going to affect the equilibrium system good because argon is an inert gas. So this would remain the same or no change. No shift, no change. Next one, the volume of the reaction vessel is decreased. So volume is decreased, that means pressure increases. So which way do we proceed? Towards the products, very good. Side with fewer moles, that would be true. Get back to that Kp. It depends. It depends on what it would react with. Say we added another gas that reacts with the bromine and it causes another side product. You'd have to look at like what product is made from that, if it reacts with it, how much of it depletes from the equilibrium system. So a non-inert gas, you'd have to really look at its reaction pathway to see what it's producing and how it's adding to the pressure differences. Does that make sense? They don't ever ask anything like that because it'd probably be way too complicated to figure out. The only ones they look at, like when you can pull ions out of solution, that decreases their concentration. That one's an easy one to do. I don't know. I've never seen one where they've added a non-inert gas and changed the equilibrium that way. But good question. On to problems. Here we go. We're going to start easy. We'll get harder as we go. Good times, right? Writing the equilibrium expression. Let's go back over that. Products over reactants. Only use gaseous and aqueous products and reactants in this expression. That means no solids and liquids. Bracket notation indicating molarities, because these are in concentrations. And coefficients become the exponents from the law of mass action. You already know all this, but here, let's review. What would be the equilibrium expression for this particular reaction?
May I go to the bathroom?
Yeah, go ahead and sign out. Do the QR code's on the back there if you want that one. You have to do the electronic hall pass.
I've never done this before.
All right, which one are we not going to include? The TI, very good. We're not going to include it because it's a solid. So no titanium. All right. Then it's just products over reactants raised to the power of the coefficients, so you should have gotten that. Bracket notation and all. Next. For this particular one, how would our equilibrium expression look? And I'm just going to tell you it's going to look a little bit different. Why is it going to look different? The solid is the only reactant. So what does that mean? No denominator. Exactly right. So it looks like this. And yes, you're going to raise the calcium to the third power because of the 3 here and the 2 here. But this is actually KSP, the solubility product for this particular one. There is no denominator because the only reactant happens to be a solid. So we will talk about KSP next week, though. All right, on to the next topic. How about this? Oops. How about this one? Which one do we not include in our expression? No water. Water is a liquid. We won't include it. So, what type of reaction is this one? This one you should be familiar and recognize it as a certain type of reaction. What kind of reaction is this? It's an acid-base. It's a Bronsted-Lowry acid-base deal. Remember, we have our proton donor, proton acceptor, and we have our conjugate acid, our conjugate base, and guess what? This X actually ends up being a Ka because this one's referring to an acid equation. Now we'll deal with these in more detail when we get to Unit 8, but they follow the same equilibrium rules as other things. Now let's talk about Kp, no brackets, only use gaseous products and reactants. Remember, no AQ here. Only things that exert gas are going to be gases. Oh, I'm sorry, the only things that exert pressure are going to be gases, so those are the only things you would put in these. Partial pressure notation, P of X, make sure you do that. So let's go ahead. What is the expression if we were looking for Kp for this one? We're still not going to include the Ti because it's solid. The titanium is a solid. But instead, it's going to look very different. No brackets. Use the partial pressures. These kind right here. Like so. Still raising it to the power of the coefficient. But this would be for Kp. Just reviewing. All right, now we're on to the basic equilibrium problems. And the best thing to do here, I know the reaction's not up here, so I'm going to write it in. So there that is in now. You have to be able to read through the problem quickly and decide what type of problem is this. Calculate the equilibrium constant K for the following reaction when it's found equilibrium concentration of ammonia 0.1, equilibrium concentration of hydrogen is 0.03, and the equilibrium concentration of nitrogen happens to be 0.04. So when we have this kind of stuff, what do we do here? Do we need a rice table?
Just plug it into the formula.
No, we don't need a rice table. Yes, this one just plugs in. Simply plug it in to the equilibrium expression. Calculate that out. K equals the hydrogen raised to the third power times the nitrogen over the ammonia raised to the second power here. Get your expression, plug and chug, and you get your K. So if you're given equilibrium concentrations, you don't have to do anything except for plug it in and solve.
this SAC, do we need to write out like K equals C, D, A, B, and then like K equals the products on top and the reactive on the bottom, and then write that out? We have to write like all steps of plugging it into the formula.
Yes, technically you should write out your expression before you plug it in, but usually the way the FRQs are set up, A will be writing out the expression. B will be the calculation part. So the way that they set it up is usually that way. Yes, go ahead.
Lay down your side.
Yes, that is correct. One significant figure, because this one has one and this one has one. Exactly right.
For example. Like usually like it's written into, but like it's dependent on significant digits, right?
Yes, so you take the concentration significant digits, and since we're multiplying and dividing, we would go with the least number.
Thank you.
Sure, no problem. All right, now, this next one is referring, it's like part B of this problem here. What is the KEQ for this reaction if it's at the same temperature as the above reaction? How do we figure this one out? What do we do here?
Don't we just do the same thing with different exponents?
Is it the same K though? Is it the same K? Look at your reactions. Compare them. What is different?
It's going to be it multiplied and it's like 1 over. It was
Switch
flipped.
places.
Oh, it's reversed. Yes, it's flipped. What else is different?
The coefficient. Right.
It was multiplied by 1/2.
It is multiplied by 1/2 too. Yes, we have that going on here. This one we have a flipping and a multiplying by 1/2. So what does that mean we do to the K value, the original K value?
We do 1 over K value
Yeah, 1
to the
over.
1/2.
Reciprocal, 1 over K, and then of course raised to the 1/2 power. Very good. That's what we do here. A lot of people forget this and they might throw this in. So A on your FRQ might be write out the expression. B might be calculate K, and then they give you a new version of the reaction for C where you have to flip or multiply. So as you can see, this is kind of a setup for an equilibrium FRQ. So yeah, this would be 1 over the 1 times 10 to the minus 4, raised to the 1/2 power, or square root it, whichever way you like to think of that, raising it to the 1/2. Very, very good. Now for the fun stuff. Guess what? Sometimes they can give you grams. And what does that mean? No, you don't want grams because that means it's extra work. And you have to do what?
Convert it to moles.
You have to convert it to moles and then to?
Divide it by the volume for molarity.
You have to convert to moles and then divide by the 2.5 liters here in this case to get the molarities. Yes, we have to get to concentration here. So yes, they could give you grams. Yes, not fun, I know. So take a moment to do it. Yes, extra work. Convert to moles, divide by volume, get molarities. Nice try. But no, it doesn't say molarity, but nice try. I guess we could pretend, but then we would get it wrong. So take a moment to do your conversions. I'll give you like a couple minutes and then we'll come back and check, make sure we're all right. All right, so here we go. Just gonna do them in order up here. We have this much PCl5. This is also another way you can set it up to make it go faster. You do the grams here, 1 mole up here. This one's what, 208.22. And then you can put the 2.5 liters there. So it's all set up in one nice little track to get your molarities. And I'm getting 2.02 times 10 to the minus 4 MPCl5. Is that what you mean by small? Here we go, this one. Phosphorus trichloride, here we go. And I'm getting 137.32 for the molar mass and 2.5 liters. And we get 6.40 times 10 to the minus 4 molar, bless you, PCl3. All right, last but not least for the chlorine. 70.90 grams equals 1 mole, 2.50 liters. And this one getting 0.0120 molar of chlorine. We end up getting those values. Then all we have to do is plug them into our KP expression, right? Or KC expression, right? KC or K, doesn't really matter. So we do K equals the concentration of our product over the concentration of our reactants. Multiplied here, set that up. And then we would plug in the values. So that's going to be 2.02 times 10 to the minus 4 on the top. On the bottom, 6.40 times 10 to the minus 4 and 0.0120. So what do we get for K? K ends up being 26.3 is what I got. Very good, thank you. What does that tell us about our equilibrium position here? Equilibrium position lies on the right. Yes, because K is greater than 1. It favors the product, favors the forward reaction. Yay! All of those things you could say about the equilibrium position. So the equilibrium position lies on the product side, favors products and the forward reaction rate. There we go. Now for this fun one. I used the same information from the previous problem so we don't have to recalculate molar masses here, but let's think about what they give us here. 250 degrees Celsius, equilibrium mixture, 2.5 liters. Flask contains the 2 reactants. Same amounts as before, reactant 1. Here's our other reactant. That means PCl5. Okay. We don't know that one. That's the one we're missing. We don't know this one. Okay. They also gave us, importantly, Kp. And they want us to find the partial pressure of phosphorus pentachloride. So, any ideas? Where to even begin here? This is a fun one, I mind you. Definitely a fun one. We need partial pressure. Kp. Partial pressure of PCl5. Any ideas? We have temperature, we have volume, we have grams that we can convert to moles. So what can we pull in and use to find our partial pressure here?
UD equals nRT.
Yes, very good. This is where we have to pull in the ideal gas equation. It pops up here
Didn't see that on the slide.
in our equilibrium problems. Because if we find the partial pressures of PCl3 and Cl2, we can use the Kp expression and find the partial pressure of the third. So here is one where we would need to use ideal gas law. But before we can use ideal gas law, we need to know the moles of our two reactants. So let's go ahead and calculate that. Do that right here real quick. You already calculated the molar masses, so it shouldn't be too hard to just do the moles here. Or maybe you've already calculated your moles. I did it all in one calculation last time. So you might already even have the moles ready to go from the previous problem. So I'm getting 1.60 times 10 to the minus 3 moles of the PCl3. And here for the chlorine, 2.12 grams chlorine. And chlorine is 70, 90 equals 1 mole. So this one will be 0.0299 moles of Cl2. Now that I have that, I can go ahead and do my PV equals nRT. PV equals nRT. I have my moles, I have my volume in liters. That's already here, so this is the 2.5 liters. The temperature is going to be the 250 plus the 273, right? Got to change that to Kelvin. So this is 523 Kelvin. We're looking for the partial pressure. Now, the question is, good question here. What R value do we have to use here?
0.08.
Yeah.
Correct. We need to use the one that has the ATM measurement because Kp is measured using ATM for the partial pressures. So this one we have to use the 0.082061 for the R. That's very important. Now let's go ahead and calculate. So starting here with the PCl5, I'm going to do that one first. For the partial pressure of PCl3.
I got 0.0275.
Sounds correct. 0.0275 ATM. Good. Now let's do the other one. What do we get for our partial pressure of our chlorine?
0.498. I think I typed it in the calculator.
Yeah, I think that one's just slightly off. I believe it's this value, if I'm remembering correctly. Yes. 0.513, 0.513, and 0.0275. Right? I think you're just one place value off.
Oh yeah, I got it.
All right. Now that we have both of these partial pressures, and we know our Kp over here, guess what we can solve for? The missing partial pressure. So let's do that. You know, Kp, partial pressure of PCl5, partial pressure of PCl3, times the partial pressure of the chlorine. Plug in. Oops. I'm supposed to plug in there. Oh, I just kind of erased some of that. Okay. So we have 0.613, missing this part, and we have our two values on the bottom. So PCl5, what is that partial pressure? Yes, 8.65 times 10 to the minus 3 ATM. Now also think about this. Does that make sense? Our K value, Kp, is less than 1. So that means the equilibrium position lies on the reactant side. So doesn't that make sense that the partial pressure of the product would be lower than the other two? Right? So you can kind of eyeball your numbers and make sure you're in the right ballpark at least. There we go, it shows up. Awesome. Now for rice charts, rice tables. I love rice. Rice is nice. Yes, we like rice. Now, being able to recognize what type of rice problem also will help speed things up. So, rice tables, if you're calculating equilibrium constant, that means they have to give you some initials and at least one equilibrium one, because you have to be able to figure out the change. Also, if they give you initial concentrations of not given any initial concentrations of the products, you assume that they are 0, so that it would go towards the products to get to equilibrium. Let's look here at an example. Calculate the equilibrium constant K following reaction. We have 3 molar nitrogen monoxide, 3 molar oxygen, and they're telling us the equilibrium concentration of the nitrogen dioxide at 2.5. So we want to set up a rice table. Not that you've forgotten, but here, reaction, initial, change, equilibrium. Sure we have that down? All right, so here, starting with this problem, I'm just going to make this my R so I don't have to rewrite it. Going to insert my stuff here. I have 3 molar to begin with of this one. I have 3 molar of my oxygen. And I have nothing to start with here of my nitrogen dioxide. However, I do have an equilibrium concentration that goes there. Now we know it's going to proceed towards the products because we start with 0 products. So it has to go towards the right, so that means our change is going to subtract on the reactant side, it's going to add on the product side. Now for NO though, what should the change look like?
minus 2x.
Correct. This one should be minus 2x. Very good. Because we have the 2 here, so it's going to be double the change. This is going to be minus x. And then, of course, this would be plus 2x here. Now that we have that, can we figure out the change?
Yeah. From the product side, you could do 0 plus 2x equals 2.5 and then solve for x.
Good. From here, we should be able to figure out our change, right? 0 plus 2x equals 2.5. So x equals 1.25. Not yet. I suppose you could, but we're just not going to, I guess. I don't know. Whatever. Wait till the end. We usually wait till the end to round.
So it doesn't get all right.
All right, so then all we have to do is plug this in here. So put in your 1.25 here. Put in your 1.25 here to get your 0.50. I believe this ends up being 1.75, but this now I would round to 1.8. Then we have equilibrium concentrations. 1, 2, 3. We can do our expression. So K equals NO2 squared over NO squared times oxygen. And that's going to be plug in. So we get 2.5 squared over 0.5 squared times 1.8. And what do we get for K?
14.
Good, you got 14. Very good, very good. Excellent, excellent. One type of problem. You need to run through it, the setup, all the rice table stuff is here. So you can set it, see that right there. See that we are going to use the products. I highlighted it in yellow in order to do the change. So that's what you would do to get your X value, your change. Then you plug it in like so. And you get your concentrations. And you plug it into your expression to get K. Very good. Now this one. Let's take a look at this one. What is the main difference here? There's only really one. It's in pressure, ATM, partial pressure. Good. So give you like 2 minutes, set up the table. So looking here, check out your rice table. Does your rice table look like my rice table? Showing here. So which chemical species can we figure out the change from? Correct. We can figure it out from the bromine. There you go. I highlighted it in yellow for you. So do that. Figure that out. 6 minus x equals 3.9. So x is 2.1. All right, so we figured that out. Now we plug it in to get our equilibrium concentrations. Yay, got those. Now we can plug them into Kp. Here's Kp, partial pressure notation, yes. Noted it's not as fun as brackets, but is what it is. Plug in the numbers. Calculate your Kp. Did you get 3.2? Yes, no, maybe so?
Yes.
All right, yes, here, yes. Okay, thank you. Now for the more difficult ones. Now we're getting into a little bit more challenging. Initially, 0.4 mole of nitrogen and 0.96 mole of hydrogen are placed in a 2-liter container, constant temperature. Equilibrium constant happens to be 7.66. What will be the equilibrium concentrations be for H2N2 and ammonia? Now, how you should recognize this problem, that you've been exposed to a lot of them now. They gave us initial concentrations for our reactants for H2 and N2. Yes, we have to figure them out because they gave us moles and liters, and we have to do a quick molarity calculation. They also gave us K, but no equilibrium concentrations. So what type of solving are we going to have to do here? Yes, we need to set up the rice table. Let's do that. But when you're only given initial concentrations and no equilibrium concentrations and you're given K, what type of solving method are we going to have to use? How do we get our X? I guess technically it's algebra.
Oh, is this the graph one?
Yes.
We have to put the x's like in the equation.
You're going to want to graph this one. You could use the quadratic formula, but you have fun with that. I'm going to stick to graphing. So, and it's the graphing is quicker than the quadratic formula here. So, you set up your rice table. First, you have to do the 0.4 moles divided by the 2 liters and the whatever, right? You get your molarities, because remember, these had to be calculated here, these two. So that's how we set up the rice table first. We calculate the molarities. Then we put in the change. Because we're starting out with no ammonia, it's going to go to the right towards the products anyways. So we take away from the reactants, but it's minus 3x, it's minus x. We're going to add 2x to the products. So then we put that in. So we have to plug in our calculator now. Here are our concentrations. Plug it in following the expression. So this goes in as Y1. This one goes in as Y2. And make sure that you look for, this one has 2 intersections as well. So you need to look for the one that doesn't give you a negative concentration. Because at first it popped up for me to giving me the larger number. And so then I had to go and find the other intersection. And let it guess for you, but you have to go and, click on each line there that are close together to find that intersection. So take a moment to graph it.
My graph is like messed up. I did something to it the other day.
See here, did anybody get your X value yet? The correct intersection? Yes, no, maybe so. I didn't get that. Yeah, that's the one I got. Solved by graphing 0.070. That's the one I got. The other one was like 0.41 or something.
I think that's just a guess.
So, you put your cursor on each line and then you do first curve, second curve, and let it guess for you, and you should get the 0.07 on your X value. But once you get that, so solve by graphing, there you go. Then you can plug it in, like so. Get your equilibrium concentrations. Right? Oh, we'll do the Q calculation one next time. But this is This is medium difficulty, because the Q calculation one is like the longest, hardest one. So we will finish the Q calculation and the multiple choice ones next week.